Welcome back. Today we're going to talk about limits to growth and planetary boundaries. So you will learn what the first part of this lecture title means and what is the origin of this first part of the lecture title. And we're going to start with this image that I've shown you many times as a representation of the fact that we have our planet as a finite system that is in a simple way very much like the sandbox that we have here. We have a limited space, we have a limited set of resources, and we can only use up those resources up to those amount that are available. And we can also only contaminate the sandbox up to a certain space until it gets essentially uninhabitable. And we also talked about the Earth Overshoot Day in the very first lectures. So we have a planet with finite systems, with finite resources in a finite systems. The more resources they use, the less they become. And there's a certain amount of resources that is regenerated over a certain time period. But in general, we as humans use way more resources than are regenerated within this biocapacity of our planet every year. And at some point, we'll just run out of resources and not having an inhabitable planet anymore. Both of these examples have a very simplified perspective on this matter. They essentially boil it down to more or less one or two different parameters or constraints. So when you look at the Earth Overshoot Day, it's essentially just at which day did we overshoot the biocapacity of our planet. So it's very simplified, but obviously it's a more fine-grained problem that is highly complex and depends on a lot of parameters. And this is what we're gonna look into more detail today. And we start doing so by looking at a also simplified equation, but then we're getting a little bit more complex. And first, we're going to have a look at the so-called Lotka-Volterra equations. You might also know them as so-called predator-prey equations. And they have at least two variables. You have, in most examples, foxes and rabbits, as represented by these two curves on the screen. And the rabbits, being red, they have a certain start population of 300, as you can see, and the population goes up. And the more rabbits you have, the more interesting this area becomes for foxes, because foxes like to eat rabbits. So also the fox population goes up. With the upwards trend of the fox population, you start to notice that the rabbit population heavily decreases, because the more foxes you have which eat rabbits, the less rabbits you have, until the rabbit population more or less collapses. What follows next? The fox population collapses as well, because there is not enough food left anymore. While the fox population collapses, the rabbits slowly but surely recover from their collapse, and then we're back in the cycle that continues again and again and again. So we have an increase in rabbits, followed by an increase of foxes, and then a collapse of rabbits, followed by a collapse of the foxes. And this very simple equation, as known as predator-prey equations or Lotka-Volterra equations, is essentially what we're going to build on for this lecture. The foundation that we will talk about mostly today is written down in this quite old book, which is called The Limits to Growth from 1972. And in this book, that was published by the so-called Club of Rome, the authors looked into different scenarios given the information they had in 1972, which were available to model how the world might change over a longer period of time. So essentially, starting those thoughts for the challenges of the 21st century that we like following in this lecture, they started this line of reasoning, the line of thoughts back in 1972 or even before that, and tried to put those into numbers, created a scientific computational model, and then made certain predictions how the world might look like at the end of the 21st century. And when they wrote this book, they already came to the conclusion, look, we're doing something that is not sustainable, we cannot continue like this. And in the book they wrote, if the present growth trends in world population, industrialization, pollution, food production, and resource depletion continue unchanged, the limits to growth on this planet will be reached sometimes within the next 100 years. The most probable result will be a rather sudden and uncontrollable decline in both population and industrial capacity. This is what they predicted 50 years ago, more than 50 years ago. And as you have already seen, we didn't really learn from that. And one of the most commonly known or prominent results of the Limits to Growth book is the so-called World 3 standard run. We'll go into detail on this a little bit later. World 3 is the model, the mathematical model that they created, and the standard run is the simulation based on that model that assumes certain standard parameters. And you have these 5 main parameters or main concerns in this model. First, the red curve, which represents the resources. So we start in the 1900s with a large portion of resources, which is then slowly but surely depleted by using it. You also have the population, which increases over time, and you have further parameters like food per capita, industrial output per capita, as well as environmental pollution. And when you run the model, start the model simulation in the 1900s and let it run for 200 years, the standard run looks as represented in this figure. We slowly but surely deplete our resources. While doing so, our population increases heavily, mostly due to using resources, but also by increasing the food per capita, as well as the industrial output per capita. But we pay a high price for that. We're not only using resources, but we're also increasing pollution. And the loss of resources, the increased pollution, will decrease the food per capita. And at some point, similar to the Lotka-Volterra equations, we see a sudden collapse or drop in population. So very similar with respect to the result. And even though the model is not time sensitive with respect to giving us precise predictions when a certain event will occur, it still gives you a very good intuition what could maybe happen if we continue as we do right now. So it's very similar to the Earth overshoot implications that we talked about. You can even go back to the sandbox example that I gave you. If you continue doing this, we'll probably have a large problem. And as I already mentioned, the model itself is quite old. It was published in 1972, so it also makes sense to think about, okay, how the assumptions that we made for the model change over time for the last 50 years or so, and how closely does the prediction of that model fit what actually is now happening in our world. So for that reason, the Club of Rome also published a series of updates. For example, as you can see here, the 30-year update, where they checked, okay, what kind of parameters could we update? Are they like still recent? And how closely does the model predict what or how the world changed so far? So there is like a series of updates reports on that. It's not just they published something in 1972 and they never got back to it. And as it turns out, it is astonishingly close, but we will also get to the point why those predictions might be a little bit difficult to put into context and how they really match reality. Before we go into more details with respect to the World 3 model, we'll first do a short detour to the so-called planetary boundaries. Because so far we have looked at sustainability related issues and especially predictions with 1 or 2 or 3 variables, Earth overshoot date, the sandbox example, Lotka-Volterra equations. And now we're moving a little bit towards a different perspective, because depending on how many variables you account for, the more complex your predictions become. And I think the planetary boundaries are on one hand a very helpful concept to understand the challenges of the 21st century in itself a little bit more better, but also to illustrate this specific fact. And the planetary boundaries are a concept that was first proposed by Rockström from the Stockholm Resilience Center in 2009. And it essentially tries to give us 9 indicators that are of high importance for the stability and resilience of the Earth's systems. If we break those indicators, then there is like a severe risk of our ecosystem failing and us triggering irreversible environmental changes. So it tries to give you a little bit of a quantitative approach to get from these abstract representations like the Earth overshoot day to more quantitative approach where you can work better with numbers. And to do so, they identified 9 indicators that they deemed to be important. biosphere integrity, climate change, novel entities, stratospheric ozone depletion, atmospheric aerosol loading, ocean acidification, biochemical flows, freshwater use, and land system change. And similar to the sustainability development goals, you have to keep all of these indicators in balance or in check and achieve a sustainable level for all of them. If only one of them fails, it still is a huge problem for us, and we might get trouble with respect to sustaining our existence. And as you can see in this extended illustration of the same figure, you can see that there is a color coding. Green means that we are, with respect to that indicator, below the planetary boundary. Yellow is that we're somewhere in this uncertainty zone where we might have crossed the boundary, and red is beyond the zone of uncertainty, so there's a high probability that we are in big trouble. And as you can see, there is a quite big difference for those indicators. So you cannot just rely on just one number or one indicator to tell you, look, we're fine or we're not fine. Because according to the Resilience Center, we have probably not really a problem with freshwater use. Even though we already discussed in the lectures that there is a problem with respect, for example, to when do we have too much or too little water and distribution of water and so on. But in terms of freshwater use, according to the planetary boundaries, we are fine. On the other hand, when it comes to biosphere integrity or biochemical flows, we're deep in the red zone, which indicates that we're in big trouble there. And you can also see that there are some indicators, too, to be precise, that have no color coding at all. That means in this particular figure that they haven't been quantified yet, because some of those parameters are very difficult to get to hard numbers, so they leave them open for now, but they still deem them to be relevant. And the reason why we discussed this, as I already told you in the introduction, is that I want to give you a little bit better understanding on how different indicators can change a model or a simulation. So the more complex indicators and parameters and variables they have, the more difficult it becomes to just interpret the results. And it also makes it more difficult to predict the simulation results that you get by executing a model.